Hello friends, a very good morning to all the students. Am I audible? Okay, fine. So friends, you remember that we are discussing the important chapter, that is the third unit, properties of the gases. And friends, all the students are requested to off their videos as well as mute themselves. So dear friends, as you are aware that in this lecture or in this particular chapter, it is the total analytical chapter, and also we will be solving several numericals for determining the properties of the gases. So for solving the numericals, you will require the scientific calculator. So friends, I suggest that whenever you are purchasing the scientific calculator, you can purchase any one of these scientific calculator. The model, that is Casio FX82MS. Dear friends, this is a non-programmable calculator which is allowed in the GTU examination. If you are purchasing any other calculator, scientific calculator, and if it is programmable, then that calculator is not allowed in the GTU examination. So what we suggest to the students to purchase any one of this model. Both the models are having the same name, but this is the older version and this is the latest version, that is the second edition of the model. So I hope the term related to the scientific calculator or the concept of purchasing the scientific calculator which you need to purchase is clear in your minds, because in few lectures only I will be completing the analytical and the theoretical aspects of this chapter, and then we are going to solve the numericals of the chapter. So whenever we are solving the numericals, you need to solve those numericals at your level, and also you need to give me the answers. Sir, in this chapter, do we have any practicals? No, there are no practicals in this chapter. Okay, there are no practicals in this chapter of the properties of the gases. So friends, let us start with the other topics of the chapter of the properties of the gases. So before proceeding further to the discussion of the newer topics, let us revise the previous topics which we have discussed in the last lecture. Let me ask you some of the basic questions so that you are getting the points. So my first question to you, can anybody state the Mayer's equation? Can anybody state the Mayer's equation? Okay, I am getting the responses from the students in the chat box. Find Cp minus Cv, that is equal to capital R. Okay, that is the perfect answer. So Mayer's equation, that is Cp minus Cv is equal to capital R, which was one of the important derivation which we have discussed in the last lecture, where Cp represents the specific heat at constant pressure, Cv represents the specific heat at constant volume, and capital R represents the characteristic gas constant. I hope you have perfectly understood that derivation. And if you remember, in the last topic of my previous session, we have discussed the names of the different non-flow processes we are going to study in this chapter. So any student can give me the names of the non-flow processes which I have discussed in the last lecture. Give me the names of the non-flow processes. Okay, fine. Thank you all. So you are remembering all those terms which are discussed in the previous lecture. Majority of the students are giving me the perfect answer, the right answer. Okay, roll number 44 has given me the names of all the 5 processes. Very good student from your side. Okay, you are remembering all the 5 names. Also, majority of the students are giving me the right answers. That is very good. So now friends, in today's lecture, you just take the notebook and the pen because today's lecture will be a totally analytical lecture. There will be several derivations we are going to make. We are going to derive tremendous equations in today's lecture. So if you are noting all these equations, then you will easily remember all these equations whenever we are solving the numericals. So let us start with the current session. So in this lecture, I am going to discuss 3 non-flow processes. The first process we are going to understand, that is the constant volume process. Then we will understand the different parameters and the different concepts of the constant pressure process. And finally, we are going to understand the third process, that is the constant temperature process. So let us start with the first process, that is the constant volume process. So friends, in this process, the working substance or the gas is contained in the rigid vessel. Hence, we are considering the boundaries of the system are immovable. Since the boundaries are immovable in the system, there is no change in the volume of the gas. And also you are seeing in the figure, since the gas is contained or supplied to the container and we are having a piston on the top of the gas, but that piston is fixed. So now we can tell that the boundaries of this system are immovable. Hence the volume of the gas will remain constant. So friends, the constant volume process, the another name, remember this name, also note down this name. The constant volume process is also known as the isochoric process. Try to remember this name because in the examination, some of the questions might be twisted and you are asked to explain the isochoric process. So remember friends, the constant volume process is also known as the isochoric process. If we are presenting the constant volume process on the PV diagram, we are seeing that this is the straight line, vertical line we are getting because we need to consider the constant volume conditions. One is the initial state and 2 is the final state. From the figure, we are seeing that there is no area of this straight line. Hence, there is no area on the volume line. So, we can consider the work done to be equal to 0. And in the next processes, you will see that we will be getting some area of the diagram, that is the PV diagram. And whenever we are getting the area of the diagram, always we will be getting the answer of the work done. As we are proceeding further in this lecture, you will understand this concept perfectly. So right now only focus on this point. For constant volume process, since it is the vertical line, there is no area on the x-axis, that is on the volume axis, hence we can consider the work is equal to 0. Now let us derive some of the equations related to the constant volume process. So I hope now you need to note down the equations so that the equations are perfectly clear in your minds. Firstly, the work done in simple terms is denoted or equal to P into dV. But when we consider the total work, that is equal to integration of P into dV, where we need to take the limits, that is V1 to V2. So friends, on integrating this term, I hope you are aware about the integration. So we are getting the answer, that is W is equal to P into V2 minus V1. Let me pause at this point and ask you, are you aware about this answer? How we have got this answer about the integration of PdV between the limits V1 to V2? I want the responses in the chat box. Have you understood how we have got the answer P V2 minus V1? I want the responses in the chat box from majority of the students. Very good. Thank you all. So getting the responses from your side. So now in this equation, since we are discussing the constant volume process, and also in the figure we have already understood that V1 is equal to V2. So substituting this value in the above equation, finally we are getting the answer, that is W is equal to 0. I hope you have understood this point. And friends, if you remember in the previous lecture, in the derivation of Cp and Cv, we have taken the work done for the constant volume process, that is equal to 0. Now I think you have understood why we have taken the work done that is equal to 0 in that case. Let us proceed further with the second derivation, that is the relation between the pressure, volume and temperature. We are already aware about the combined gas law that states that PV by T is equal to constant. If I am writing this equation at the initial stage and the final stage, then I can write down P1 V1 by T1 is equal to P2 V2 by T2. Since the volume is constant, we can write down V1 is equal to V2. So both these terms are cancelled it out. So finally we are getting the answer, that is P1 by T1 is equal to P2 by T2. So this is the second derivation. Now the third one, that is the change in the internal energy. Dear friends, if you remember, we have already derived this equation in the previous lecture, that is the relationship between Cp and Cv, and I have highlighted that point, that whenever we are asked to find out the change in internal energy throughout this chapter, there is only one equation, that is delta U is equal to mCv T2 minus T1. So I hope you are getting the points, you are noting down these equations. Let us proceed further. The amount of heat transfer according to the first law of thermodynamics, I can write down Q is equal to delta U plus W, but W is equal to 0, so Q is equal to delta U. So same equation I can write down for Q also, or in another sense I can use the equation amount of heat that is equal to mc delta T, but we are considering constant volume. So we are taking the specific heat at constant volume conditions. So I have written that is mcv T2 minus T1. So dear friends, I hope you have understood up till this point. Let us proceed further with the last derivation of this topic, that is the change in the enthalpy. So friends, if you remember, according to the definition of enthalpy, that is H is equal to U plus PV. Writing this equation for states 1 and 2, I can write down H1 is equal to U1 plus P1V1 and H2 is equal to U2 plus P2V2. Now if I want to have the change, so change in enthalpy, that is delta H, that is equal to final enthalpy minus the initial enthalpy, that is H2 minus H1. Substituting the equations, I am getting this answer, that is U2 minus U1 plus P2V2 minus P1V1. Remember friends, the product of pressure and volume, that is not the work done, that is the flow energy. So this P2V2 represents the flow energy at the final state and P1V1 represents the flow energy at the initial state. Now if we are considering the properties of the gas, since we are using the perfect gas, we can use the characteristic equation or the perfect gas equation, that is equal to PV is equal to MRT. At one point I can write down P1V1 is equal to MRT1. At 2 I can write down P2V2 is equal to MRT2. So substituting this value of P2V2, that is MRT2, P1V1 that is MRT1, and U2 minus U1, that is nothing but delta U. So delta U we have already noted, that is MCV T2 minus T1. I hope you have understood up till this point. I want the responses from the students. I hope you have understood up till this equation, how we are getting the answer. Substituting all these terms, getting the equations from the previous topics which we have already studied. Okay, fine. Thank you all. So now what we are going to do? We are going to substitute the value of capital R from the Mayer's equation. So substituting the value of capital R, that is equal to Cp minus Cv, opening the bracket, elaborating the bracket, two of the terms will be cancelled it out. If we are doing the mathematical calculations, then you will observe that two terms will be cancelled. One is positive, one is negative. That positive negative terms will be cancelled and only one term will be remaining. That is our final answer. So the final answer, that is the change in enthalpy, that is delta H is equal to mCp T2 minus T1. I hope you are getting this answer. If you are calculating in your notebook the derivation. Okay, getting some of the positive answers from the students. Very good students from your side. I want some more responses. If you are getting this answer, that is delta H is equal to mCp T2 minus T1. Okay, fine. Thank you all. Thank you very much for giving me the perfect answers, the positive responses. Okay friends, so this was about the discussion related to the first non-flow process, that is the constant volume process. Now in the similar pattern we are going to discuss the second process, that is the constant pressure process. So in the constant pressure process, the working substance or the gas is contained in the rigid vessel. But in the figure we are seeing that now the piston is a movable piston, and when the gas is heated, because of the expansion of the gas, the weight above the piston is lifted to a newer position. Another name of the constant pressure process, that is isobaric process. Remember friends, the another name of constant pressure process is isobaric process. If we are presenting this process on the PV diagram, then we are seeing that this is the initial state 1, this is the final state 2, drawing the horizontal line, and now we are getting the area of the diagram on the x-axis or the volume axis. And since we are getting this area in the diagram, this area represents the work done. So in the constant pressure process, we are going to get some of the answers related to the work done. But in the constant volume process, since there was no area, we have considered the work done, that is equal to 0. So now let us proceed further with the derivation. The amount of work done, the same equations we are going to use, that is work done is equal to PdV. Total work done, that is W is equal to integration of PdV between the limits V1 to V2. Taking P as the constant term, integrating between the limits, we are getting the answer, that is W is equal to P V2 minus V1. Remember friends, in this case the work done is not 0 because we are getting the area of the diagram, so we will be getting some answer of the work done. So the answer of the work done we will be getting, that is W is equal to P V2 minus V1. Proceeding further, the relationship between pressure, volume, temperature, using again the combined gas law, PV by T is equal to constant. Writing the equations at states 1 and 2. Since we are discussing the constant pressure process, P1 will be equal to P2. Cancelling both these pressures. So I can write down V1 by T1, that is equal to V2 by T2. Dear friends, if you remember, this equation is of the Charles law. I hope you are remembering that point, because in the Charles law also we have taken the pressure to be constant. So we are getting the answer, that is V1 by T1 is equal to V2 by T2. Now friends, proceeding further, the change in the internal energy, we are having only one equation, the standard equation for the change in internal energy, that is delta U is equal to mCV T2 minus T1. Let us proceed further and find out the amount of the heat transfer. So according to the first law of thermodynamics, Q is equal to delta U plus W. Substituting these values of W, that is equal to PV2 minus V1, and delta U is equal to mCV2 minus T1. Substituting these equations in the first law of thermodynamics, doing some mathematical calculations. If you observe and do the mathematical calculations, you will be getting this answer, that is Q is equal to mCp T2 minus T1. Or in simple, if you want to remember, since we are discussing the constant pressure process, the amount of heat transfer Q is equal to mc delta T. But for the constant pressure process, we are considering the specific heat at constant pressure. So we are writing down as C. Very simple to understand. Moving further with the last point, that is the change in enthalpy. The same method we are going to apply in this case also. As per the definition, H is equal to U plus PV. Writing these for states 1 and 2, H1 is equal to U1 plus P1 V1 and H2 is equal to U2 plus P2 V2. This is just a revision of the terms which we have discussed already in the first process. So change in enthalpy, that is delta H is equal to H2 minus H1. So that is equal to U2 minus U1 plus P2 V2 minus P1 V1. U2 minus U1, that is equal to delta U. Substituting the value of delta U in this equation. Substituting the value of P2 V2 minus P1 V1, that is MR bracket T2 minus T1. Taking the Mayer's equation, substituting capital R is equal to Cp minus Cv, elaborating the brackets, again two terms will be cancelled out, the positive and the negative terms, and finally we will be getting the same answer of delta H, that is mCp T2 minus T. Dear friends, I hope you are understanding the points, you are understanding the derivations, how we are getting the answers in the different parameters for the particular process. I want your responses in the chat box if you are understanding the points. The method will remain the same, only there will be some manipulations, modifications in some of the equations. Okay, fine, getting the good positive responses from the majority of the students. Okay friends, so we have perfectly understood the two non-flow processes, the constant volume process and the constant pressure process. And also in the both the processes we have derived several equations. Let us proceed further to the third process and the final process of this session, that is the constant temperature process. Note down this point, it is one of the important question which is generally asked in your examination. So focus on this point of the constant temperature process. So constant temperature process, the another name, that is the isothermal process. And from the name only we can understand that in this process the temperature of the gas will remain constant. Since the temperature of the gas remains constant, we can easily apply the Boyle's law, because in the Boyle's law also we are taking the temperature parameter to be constant. So thus for the isothermal process or the constant temperature process, the law of expansion or the compression on the PV diagram is a hyperbolic curve. The figure which you are seeing, the diagram, the pattern which you are seeing, that is a hyperbolic curve, because this process follows the Boyle's law, and for the Boyle's law we have already understood and studied P is inversely proportional to 1 by V, or we can write down PV is equal to constant. Since this process follows the hyperbolic process or the hyperbolic diagram is obtained through this process, hence the third name for this process, that is the hyperbolic process. So dear friends, try to focus on this point, try to remember the different names. I am repeating once again, there are three names for this process. The first one, that is constant temperature process. The second one is the isothermal process. And the third one is the hyperbolic process. So these are the three different names of the same process. So let us proceed further in calculating the equations, that is amount of the work done. So we are using the same equation, work done, that is equal to PdV. Total work done, that is integration of PdV between the limits V1 to V2. Now friends, remember this derivation for isothermal process. Since it is following the Boyle's law, PV is equal to constant. So I can replace P is equal to C upon V, where C is the constant term. So the constant term will be removed from the integration. Substituting the value of P, I can write down W is equal to integration of C by V dV between the limits V1 to V2. C is the constant term, so it is removed from the integration. So this is a simple integration. Integration 1 by x dx. So dear friends, what is the answer? Integration of 1 by x dx. Integration of 1 by x dx. Okay, majority of the students are giving me the answer log x. Okay, so this is the error which majority of the students will be making also in the examination. So remember friends, it is not the log x, but we need to consider that is ln x. Or if you are writing down, then we need to write down that is log to the base e. So in order to be not getting confused during the examination, just remember integration of this value. The final answer will be on integration, we will be getting that is W is equal to C ln V2 by V1. Perfectly write down this point in your notebook also and perfectly remember, do not go in the concept of log. We need to note down that is ln, and while making the calculations we will be directly using the ln term for the calculation. So I hope you have understood up till this point. So W is equal to C ln V2 by V1. So now in place of C, I can substitute the different terms. Since this process follows the Boyle's law, I can write down C is equal to P1 V1, and in place of P1 V1, I can also substitute that is MRT1. Also, I can write down C is equal to P2 V2, that is also equal to MRT2. I hope students you are getting the points. You are understanding the derivation, because it is one of the important questions can be asked in your examination. I want your responses in the chat box. Are you getting the points of the derivation? Are you getting these answers? Are you understanding the concepts? Okay, fine. Thank you very much. Thank you students for your answers in the chat box. So proceeding further, the relationship between the pressure, volume, temperature. So again using the same pattern, combined gas law, PV by T is equal to constant. So I can write down P1 V1 by T1, that is equal to P2 V2 by T2. Temperature remains constant since it is constant temperature process. So T1 and T2 will be cancelled out from both the sides. So finally we are getting the answer, that is P1 V1 is equal to P2 V2, and if you remember, this is the equation for the Boyle's law. Now friends, proceeding further, the change in the internal energy. So let me ask you, what will be the answer of the change in the internal energy for the constant temperature process? What will be the change in internal energy for the constant temperature process? Very good students, the perfect answer from the majority of the students, totally impressed from your answers. The answer for the change in the internal energy for this process will be equal to 0. Let us see how we are getting this answer. So we are already having the equation for delta U, that is delta U is equal to mCv T2 minus T1. but constant temperature process. So T1 is equal to T2, hence we are getting delta U is equal to 0. Since the change in internal energy is equal to 0, I can write down U1 is equal to U2. So I can write down, so during the isothermal operation, the change in internal energy is 0. Hence, this process can also be considered as the constant internal energy process. Now friends, let me ask you, what will be the amount of heat transfer for this process? What will be the amount of heat transfer Q for this process? Okay, here there is the confusion I am getting from the students. Some students are giving me the answer that is 0. Dear friends, remember that the heat transfer is not 0 in this case. Okay, so try to understand the logic in the isothermal process. Try to understand the equations. According to the first law of thermodynamics, we can write down this equation Q is equal to delta U plus W. But in this equation, now we will substitute delta U is equal to 0. We already know this value. So finally, we will be getting the answer, that is Q is equal to W. And we have already derived the derivation for W. So whatever answer we are getting for W, the same answer that is for Q, amount of heat transfer, it will be not negative, it will be the same answer. Okay, if we are getting the terms, because here we need to consider the boundary condition, so Q will be equal to W. The mathematical calculations. Now friends, let me ask you, what is the change in enthalpy, that is delta H, for the isothermal process? What will be the change in enthalpy delta H for the isothermal process? Very good, perfect answer from majority of the students. The standard equation for delta H, that is equal to mCp T2 minus T1. But here again the temperature remains constant. So we are getting the answer, that is delta H is equal to 0. So remember friends, if you are solving the numerical for constant temperature process, directly you can write down the change in internal energy, that is equal to 0, the change in enthalpy, that is equal to 0. But whenever you are writing down the theoretical answer for this process, you need to justify the point how we are getting the answer, that is equal to 0. That means first we need to note down the standard equation, then we need to consider temperature remains constant, and writing this term, now we will be getting the answer, that is equal to 0. Okay friends, so with this I am concluding the session from my side. Thank you for watching this session. Have a nice day. Now the platform is open for your doubts to be solved. If any questions from your side, because we are having few seconds left in the meeting, so any question from your side you can ask me. Okay, roll number 56. In constant pressure process, heat transfer, very simple equation, Q is equal to mc delta T. But C is the specific heat. Since it is the specific heat and we are considering constant pressure, so we are considering the specific heat at constant pressure. So we are writing down the amount of heat transfer, that is Q is equal to mCp bracket T2 minus T1.